A big welcome back to the Resources Conservation and Recycling webinar program. My name is Mitchell Jones. I'm the Outreach Editor at Resources Conservation and Recycling. I'm your host for today, and it's a pleasure to have you with us on this fine day in Europe. Maybe it's a night for you other people somewhere else, or a morning. So just a few brief notes before I introduce our speaker for today on the actual program itself. So this is the English language version of the Resources Conservation and Recycling webinar program. We usually run this program every second Thursday at 10 o'clock a.m. Pacific time. And this program, the scope of this program essentially matches the scope of the journal. So we aim to really run a balanced program, and we aim to equally represent, or we aim that all elements of the scope are equally well represented in the program. We don't have a specific bias for certain topics. We want to really spotlight research from all different aspects of our research field and the research scope of the journal. The only thing that we do try to do is maintain accessibility. So we want these programs to be something that everybody can take something away from. Even if they're perhaps working in an adjacent area, we have our journal, as scoped as it is, and it is scoped to a specific research area. There are facets and aspects to those different subtleties of those research areas, which mean that we all, although we work adjacent to each other, we perhaps don't necessarily know the nitty-gritty details of each other's specific research fields. So we ask that the presenters try to refrain from using too much jargon, too much research area specific terminology, and that they provide a sort of broad overview, a short introduction to the research area, also to celebrate the research areas of our peers, and perhaps learn something new from each other. So that is one aspect that we do emphasize. Now, registration for the program is necessary. You can register using the links that are circulated at the end of each month in the Resources Conservation and Recycling newsletter. You can also find those links on social media. So if you go to our official LinkedIn page or Facebook or X page, you can find registration links for this program there. The other place you can find them is on the official Resources Conservation and Recycling website from Elsevier. So if you go to the Elsevier website, the Resources Conservation and Recycling official page from Elsevier, you will find there the About menu, and in that menu, you will find the webinar calendar. In that webinar calendar, you will find a list of all of our distinguished guests that we've had join us in the past, as well as our future presenters. Future presenters, there you have the registration links, and for our guests from the past, you have a link to their archived YouTube presentation. So all of these events are archived to YouTube. So we also have on-demand viewing if you're interested in watching something after the event. Perhaps you are unable to attend an event in person. It's all there. It's also live streamed to YouTube. So if you prefer to watch it on YouTube than Zoom, you are more than welcome to do that. The final point is that we really do want this program to be a valuable asset, an opportunity for discussion, scientific communication among our research community. If you have feedback to help us improve the program, perhaps there are things we could do better, things we're doing well, or any feedback that you may have, please, we want to hear it. You get a survey link at the end of this program, as you do every program. It's just 8 short questions, and we won't take you more than a couple of minutes. If you have the time to fill in that survey, we do take it seriously. We do try to run a program that is useful to our research community. So, bringing us to the program for today, we've had our welcome address. I'm going to provide a short introduction to the journal now, followed by an introduction to our speaker, Mariano, who we are very fortunate to have with us today. I'm then going to cover a few admin aspects of how things are going to work. Then we're going to have approximately 20-minute presentation from Mariano, followed by 10 minutes or more of question time. We're flexible on the question time, also on the presentation time. And then a few closing remarks, information on the next event that will be occurring in this program. So the journal, perhaps you are already familiar with resources conservation and recycling. It's an Elsevier journal. I think the scope and our research interests are quite clear from the name, resources conservation and recycling. The key points really the key points of interest in our scope are systems-wide strategies, technological, economic, institutional, and policy focus, resource management practices, conservation, recycling, and resource substitution, resource productivity improvement, restructuring of production and consumption profiles, and transformation of industry. If you have any top quality research in those research areas, then please consider submitting it to our journal. A few points on the administration side of things. If all communication could please be in English, this is simply so that we have a bridging language that we can use to all communicate with each other. We also have closed captions available. They are currently running. You can also find them in the archived YouTube version of the presentation. These are there in case you potentially want to watch the webinar without audio. I recently read that about 80% of electronic content online, video content, is actually watched without audio. So feel very free to use those captions if you feel fit to do so, if you'd like to do so. Or perhaps also if English is perhaps not your first language and you might benefit from some captions, then feel very free to use those. They are there for you. Please post any questions that you may have in the Q&A during the presentation. I really do strongly recommend that you do this. That's the main point of having a live event like this, where you can actually interact with our speaker rather than a podcast type thing or something like that, where you would not have the opportunity to do that. So if you do have any questions, please feel very free to ask them during the presentation or during the question time also. We also offer the opportunity for you to speak directly to the presenter. If you would like to ask your question in a more old-fashioned way, or perhaps a better way, a more personal way, you are very free to ask using your microphone and camera, or just your microphone. You just have to indicate you'd like to do that with the raised hand reaction tool in your toolbar. And if time allows, we'll be very glad to welcome you onto the floor to ask your question in person to Mariano. That brings me to our introduction of our speaker. So we are very fortunate today to have Mariano MARTÍN with us from the University of Salamanca in Spain. His presentation is going to be on tracking end-of-life stage of chemicals, a scalable data-centric and chemical-centric approach. So Dr. Martín is full professor of chemical engineering at the University of Salamanca and leader of the Sustainable Processes and Products Lab. He graduated with honors in chemical engineering, receiving the Outstanding Thesis Award in 2008. He joined Procter & Gamble, where he led the last challenge in the laundry business, for which he obtained the Procter & Gamble Award for its outstanding contribution to modeling and simulation. He was Fulbright Scholar under Professor Ignacio E. Grossman, before accepting the challenge of building a process laboratory in the oldest university in Spain. Professor Martín was included within the top 2% researchers in chemical engineering in the ranking performed by Stanford University. He has authored over 180 papers in peer-reviewed journals, H-index of 40 from Scopus, 55 book chapters, 2 monographs or monographic books, and 3 textbooks for Elsevier, Springer, and CRC Press. He is evaluator of research proposals and editor of journals such as Chemical Engineering Science, Journal of Cleaner Production, Latin American Applied Research, Process Integration and Optimization for Sustainability, and the International Journal of Green Energy, among others. So thank you so much for being with us today, Mariano. It's such a pleasure to have you with us. I will now stop sharing my screen so that you are able to share yours for your presentation.
Thank you very much for the kind introduction. And And thank you, the journal Resources Conservation and Recycling, for giving us the opportunity to present you part of the work of the PhD thesis of José Daniel Hernández, who is also in the audience. And this thesis was co-advised by Dr. Gerardo Ruiz Mercado from the US EPA and myself here at the University of Salamanca. And today we're going to be talking about tracking of site and of life stage of chemicals, scalable data-centric and chemical-centric approach, which was published in this journal basically last year. So one of the things that we have to be paying attention is the fact that industry and all the chemical companies are interested in the risk evaluation of the chemical products that they produce, basically because they want to produce something that is safe and is safe for the people and for the environment that we are. Apart from the fact that the companies are interested in that, the governments can make use of those risk evaluation, basically because in the end, from another point of view, the governments will also have to pass laws in order to be able also to make sure that the operation of the countries are safe in terms of human health and environmental risk. In all the way from the manufacturing of any product to the end of life, in the end, we are tracking data. We are tracking material flow inventory data that will, at some point, allow us to evaluate the exposures, the releases of those chemicals, and how they affect the human health and the environment. So the idea is that we need to use those data in order to be able to develop this chemical risk evaluation based on the result from the entire sector. So, however, we need to recover a lot of data. Actually, that's the main issue. So in the end, we have to start identifying the facility that generates the chemical, and it doesn't matter if that chemical is going to be treated in that facility or going to be processed in an off-site end-of-life management facility. In any one of the stages, we can have direct environmental releases, inter-industry sector transfers, transfer to commercial and consumer activities after recycling. But the main important issue is the fact that we have to do this for any single chemical in the market. And we're talking about thousands of them. This is really time consuming. Imagine that we have to produce a report for every single chemical. Apart from that, there is no complete traceability of the information of the different stages and paths that the chemical suffers and goes through along the supply chain. There's uncertainty in the data, and the databases that collect that information, at some point they are not standardized. So the idea behind all this work is to develop a robust data methodology to address the complexities of this chemical risk evaluation. So the idea is to be able to develop data-driven models that will allow us to estimate, to determine exposure scenarios, environmental releases, so that we can automatically generate this chemical risk evaluation at end of life. One of the main issues is to extract the information from the different databases available and transfer those data to something that is useful for anyone to produce those models. So that's the pipeline of the data from the raw data in the databases to something in the form that can be used to produce the model. So to get to the point of this presentation, the work started by tracking their chemicals from the end-of-life material generation facility to the recycling energy recovery, treatment, and disposal facility, RETDF. Basically, we consider two different scenarios. The possibility of an intermediate entity, worker, that actually deals with treating or managing the waste, or the direct transfer of the waste to the facility. And we identify different possible environmental releases: stack air, fugitive air, on-site surface water, on-site soil. So for that, we rely on CILO US publicly accessible data sources and regulatory documents. Those were our data. And we put the methodology, the data engineering at the level of facility to track the chemical from the generation to the end of life. And we also use those data in order to compute the emission factors. We rely on the toxic release inventory from the US and the classification of the chemicals in North American Industry Classification System, NICS. However, what we have to pay attention also is to the fact that who or which is the facility that actually treats the waste. They are pollution abatement units, technologies that are in charge of processing waste before that stream is released to the environment or to recycle. So for this, we have to go in a deeper stage, basically from the process level to the unit level, to analyze how these units work. Again, we use a similar methodology. Use US publicly accessible data sources, regulatory documents, as well as the technical data, technical literature for those pollution abatement units. Basically, the yield, the capex, the investment cost, and the operating cost. The methodology is also based on data engineering, but on a more detailed level, which is the technologies. The idea is to track that flow and be able to identify which is the potential candidate, the technology that will allow us to treat depending on the flow, depending on the concentration of the chemicals in that waste stream. That is also generating models for the design, selection of the pollution abatement unit candidate, or the design of the sequence of pollution abatement units that will allow us to treat. In a third effort, what we did was to integrate both previous work. On the one hand, we had the facility level, and on the second hand, we had the pollution abatement units level. However, in this particular case, what we pay special attention is to grasp the potential of post-recycling scenarios that a chemical may have after recycling. What happens after recycling? That stream can contain chemicals of different levels that are going to be sent back to the facility. What is the effect of those? And again, there's another issue, which is the uncertainty in which processing that waste before sending it to the end-of-life facility. So everything is putting basically the background for what we are going to be presenting today, is the fact that in order for database models to be more generic, better with a more applicability, higher applicability domain, we need to go beyond US data only. And most of the data, most of the models developed before were developed just for data from a specific moment in time. So we wanted to focus and extend the work with cross-year and cross-country data, so that we were able to capture the regulatory requirement changes over time and across countries, because that's the only way we can widen the applicability domain of our previous. Our initial focus was to analyze the pollution release and transfer registers, the PRTR, belonging to OECD member countries. We consider three criteria to select which ones to evaluate. Written in English, because it was easier to get the information from the same language. Chemical-centric, because we want to track the chemical. In some cases, if the databases report just a stream of waste, we are not able to identify what's in that particular waste stream. And the data granularity, to see which is the level of detail of our analysis. And we, based on those three criteria, we base our analysis in three cases: Canada with the MPRI database, the US, we already commented the TRI database, and Australia. What is the kind of data that we were gathering out of those databases? The transfer class, we will talk a little bit and define what we mean by that. The transfer flow of the different chemicals, the flow reliability score, we will discuss on those on that definition in the next slide. the reporting year, because we want to go across years, the name and identification of the chemical, the industry sector, the location, and the identification. Just one simple example of this is the case of ethylbenzene. In this particular case, we are dealing with the ethylbenzene from the manufacture of chemicals. The sector is the manufacture of chemicals and chemical products. And for this slide, we just consider three destinations: the recycling, the landfill, and energy recovery. And we see that the kind of flows that we are able to gather, to collect, is the minimum, the average, the median, and the maximum flows. And for example, we see how, for the case of energy recovery, the maximum flow is 2 times that of recycling, while the amount of flow that goes to landfill is relatively small in this particular chemical. We've mentioned the fact that we have to be aware of how good the data are. So this is the mission of the reliability score. We used the Edelin and Ingersen methodology back in 2016. It was published, that classifies the data into five classes. Class 1, verified data based on measurements. Second, verified data based on a calculation, or non-verified based on measurements. Class 3, non-verified data based on calculation. 4, estimated by an expert. From 4 onwards is data that is basically something we cannot rely on. And it is important for us to define what is the level of trust of the data that we want to be considering. This is the summary of the data for all the 3 cases, the US, Canada, and Australia. We see that 50% is reliability score 1 to 3. Almost 90% is to 4. In the supplementary information of this paper, you also can see how the different data for the 3 countries is classified. Another important scenario we have to consider is the class imbalance. This is the kind of problems we find analyzing the data. So if we go to the left, we see 10 generic end-of-life transfer classes: recycling, storage, landfill, energy recovery, destruction, storage, underground injection, and surface impound. If we pay attention to the last 3, we realize that the data, the amount of data available for these 3 is 1% or below. One of the important things behind this is the fact that if we don't have enough data, the model developed out of that can misinterpret the data. If we don't have data, the fact that the residue is stored is possibly the model is not going to select the store basically on the statistics, basically because most of the data that we have say that this is not going this way. In order to avoid this class imbalance, instead of using these 10 classes, we could use the 5 classes to the right, in which instead of the classification before, we go for energy recovery, sewage, treatment, recycling, and disposal. And we realize that in the worst case scenario, the class with the lowest amount of data at least have 10%. This is something that is important because in this case, we have to be able to select one or the other classification just to avoid that our future model will behave bad, basically because we don't have enough data. It can happen the opposite. Basically, it can happen that we have most of the data in one class and the model can just literally select that transfer class, basically because 90% of the data is there. So just with this introduction of the kind of problems that we found, we present here the analysis of over 3 million records reported in the different databases for the 3 countries. And we can take a look at how the different countries process the waste. For instance, Canada presents over almost 25% of the waste goes to recycling. We consider Australia, we realize that almost 40% is landfill. In the US, most of the 7 transfer classes, extraction, energy recovery, landfill, and so on. Most of them, they are basically equal, but for the last three, as we presented before. One of the things we wanted to do, and actually what our analysis allowed, was to identify this concept of data drift. We have data all the way from 1987 to 2020, and we see that in 2005, there was the so-called green chemistry boom. What happened with that? There was a lot of attention and a transformation into from extraction to recycling. And that's resulted in the change in the distribution of the statistical data. So basically, we see how from we move to a larger amount of data that goes that mentions that we. Apart from this data drift, we also have the concept drift. Basically, because of this boom, because of the changes in the technologies, the changes in the yield, the cost. Also, because of this boom, certain technologies started to decline while others rose. For instance, sewage started to decline from representing 40% back in 1987 to less than 10% in 2019, while in recycling goes the opposite, from 7% to 25%. Basically, because there are people were more willing, the facilities, the companies were more willing to implement technologies that were already validated, that had a good public image, or they were validated already. This also allows us to identify the statistical condition distribution. This is important because in the end, what our analysis allow us was also to evaluate when there was a change. So basically, there was a second stage. First, we identified the year that something happened, and later we can relate that year with a law that passed, an event, an international event, or something national that happened that represented or somehow could be could result in a change in the flows, a change in the technology that was used for tracking. So here we present also out of 640 something chemicals, 6 examples of how the total material transfer modify over the years. If we start by the dichlorofluoromethane, around 2021, stopped being reported in the US from 2002. Basically, we don't have data from Australia, from Canada, and the US stopped. So this we can go with this information to the history books of the law to see why. Another thing is another example is the carbon monoxide and the methyl carbinol, that in the first case it was only reported in Australia, and it was reported for a few years, close years to 2020, the last year of the information that we had available. While in the case of the methyl carbinol, we realized that it was reported in Canada for a few years and stopped by 2019. Another example is butanol, which stopped being reported in the US, but Canada continued reported all the way till to the present day. Another important result that we could find was the fact that, for instance, we found how, in the case of hydrochloric acid, the amount of data, the amount of residue transfer changed from the US to Canada and to Australia with different levels in each case. And in the particular case of Australia, you see the year 2018 where there was a peak. So you identify the something happening. And for the carbonic dichloride, you realize that the data in the US, the data reported show small total flow, while in the case of Canada, there were a few years with non-reporting scenarios, while most of the others reported a large amount. So just the last slide of results show how PRTR allow us to identify the 10 industrial sectors with the largest amount of chemicals. The sectors were extraction of crude, manufacture of chemicals, pharmaceuticals, chemicals and chemical products, refined petroleum, electrical equipment, and so on. And there are a couple of particular things. Back in 2000, there was a peak related to mining, while in sector 1, you see from 2003 to 2012, there was a peak. And another thing that allowed us to identify was the particular transfer class associated to each one of the sectors. Most of the sectors have recycling as the most typical transfer class, but if we pay attention to sector 2, for instance, we have landfill and recycling. Sector 2 is manufacture of metals. If we go for sector 4, chemicals and chemical products, it's a little bit more spread into destruction, energy recovery, or other disposal, and of course recycling and sewage. If we go for the last one, waste collection, we have recycling, but we also have energy recovery. So with this, we want just to come to the conclusions of this last part, and before the general conclusions, actually, the applicability domain for data-driven models require more data in terms of more years involved in the analysis and across-country data. We were able to capture and identify changes in the regulatory information, the regulatory laws, and the supply chain changes over time, and also that our tracking framework can also be connected to our resources. And the general conclusions, basically what we try to do is to use a data-driven methodology in order to help develop these reports that for the chemical risk analysis, that in any other case, you have to do it by hand, one after the other. It is possible to identify and estimate potential chemical end-of-life exposure scenarios and releases, and allow us to evaluate if the regulatory compliance is satisfied. We hope that this work has contributed to the state-of-the-art of data-driven modeling, actually for the environmental regulatory, decision-making, design of processes to treat waste, and so on. With this, I'd like to thank you and thank the funding, the EPA, the Oak Ridge Institute, the Banco Santander. To the left of the picture, you see Daniel, who is in the audience, so if you have any questions, you can also address him. Gerardo, the second picture, and the third one, and also members of the group and some friends, when we presented some of this work in the ASCHE meeting back in 2019. Thank you very much for your attention, and if you have any questions, we will be happy to take them or to try to answer in any way. Thank you very much.
Thank you so much, Mariano, for such an interesting presentation. You know, I think that this is, for us, this is a first in our webinar program, and it's also very interesting for me because I work in a different area, but the concept of chemical waste, right? Because we're always thinking about, often on people's minds are things more like, you know, the things that end up in the news about plastic waste and but this is such an important and interesting opportunity for us to talk about this particular type of waste, which is actually very significant because obviously these kinds of waste can also be have adverse effects on the environment because they are chemicals. So absolutely. I will just take this opportunity now to say that the Q&A is open. If there are any questions, feel very free to ask. But in the meantime, while people think of questions, if they have any, I actually had a few questions that I wanted to ask, or more. There's some general discussion points that I wanted to bring into this to try and bring in that also a bit more that perspective for people who may not necessarily know the area that well. So the first thing I wanted to you did such a good job of bringing that into it. You mentioned some chemicals in there, so and also some quantities of those chemicals. But I just wondered if you maybe wanted to briefly provide some. I also saw in your last slide there you provide some general sector categories for the different types of chemicals, but I just wondered if you wanted to start out by talking about briefly the types of chemicals we're talking about, the quantities that we're talking about, and then link that to why these chemicals are actually important for our society. to operate?
To tell you the truth, actually, our target was all the chemicals. Basically, because the main issue behind all this work is that so far before, there were a lot of databases just gathering data in different ways. And lately, because of the possibility of using all these data-driven methodologies and techniques, we are able to analyze all those data. So what we are interested in is not only a chemical, but to produce the methodology that will allow us to track the chemicals, any one of that, and later, if one sector is interested in us to pay more attention and produce a report on a particular chemical, we can do it. But the methodology allows us to go to the databases, analyze all the data available in US, Canada, track those data, create those reports, generate models that will allow us to evaluate the exposure scenarios, the amount, the releases, the design of the units, depending on the waste. So actually, we presented just some chemicals because for us, it was interesting to present how, for some reason, one country decided not to report that. Why?
Mm-hmm.
Okay, so we can use that data. That is basically, you remember, I mean, just imagine you have millions of numbers there, and it's really difficult to identify what's going on. By processing those data, we can see, okay, this particular chemical, freon, basically one of the ones typically very important in terms of ozone layer deployment and so on. Actually, you see it. Why? Maybe because it was people stopped using it. So as a result, the government decided not to track it anymore because it already represented just a small amount or a small contribution anywhere. Also, because from country to country, there are laws, regulations that are more strict than others. So that affects which is the chemical that is reported. So that's also part of the results. Okay, you see how certain countries decided to track one chemical, some others not. Why? Actually, to go back to the legislation, you go back to policy making. In the end, we can help. In this case, it was the US EPA, environmental agency from the US, was interested in having these tools so that they could evaluate how good the data were. Actually, I was mentioning, basically the problem is if you don't have enough data, how your model is going to suggest one particular treatment. If you don't have data, you should not be using that class in order to create a model that will say, okay, if you have this amount of raw material or waste with this composition, why don't you use the storage? If you have a lot of data that says storage, maybe the model suggests storage, just basically you have a lot of data. Or the opposite, because you have just a few data, the model can somehow cheat you to say, okay, just if it's really small amount, why don't you store it? You store it, why? So basically, this is the kind of analysis of the data, because the following work after this was actually preparing those models to identify what should you do because of the source, because of the flow, because of the composition, right? So basically, exactly what we try to do is to prepare the framework so that instead of preparing the risk analysis of one chemical, we could develop all reports automatically just by processing data. In particular, you can focus on one sector. This is something that can be done. You only have to go to the models. It's something I want also to mention to the public. All the models are free. They are in the GitHubs. They are cited in the paper. So you go to the GitHub, you click there, and you see the models in Python, how they were coded, how that code was able to collect the information and prepare all these figures that we presented.
And maybe, so you were just talking then a little bit about, so did you, well, first of all, perhaps, you mentioned different end-of-life options for these chemical wastes. Perhaps you could provide, for people who are not so certain or don't understand or not so familiar with the research area, Which of these, what's the best end of life options for these chemical wastes, generally speaking, from an environmental perspective?
For instance,
And then,
sorry.
yeah, no, and then how this chemical risk evaluation and these processes in terms of end of life are varying by country. You said some are doing better than others. Some have more relaxed legislation, different legislation.
Basically different. So
Mm-hmm.
one thing is related to the kind of sectors that are established in the country. So if you have a strong chemical industry, you have a strong appliance industry, you will have different flows, amount of flows. So basically because are the waste that you are generating. But in the end of life means that if you are at home and you wash your dishes, that water goes to wastewater treatment plant. So basically that's the end of life of that waste. But we don't want to be treating just waste. So what is in the waste that goes in the water? Is food. What kind of chemicals are in the food? So that's the granularity and the fact that I mentioned in one of the slides. We don't want just, this is the chemical-centric. The chemical-centric means that we have the list of chemicals involved in that particular flow. So as well as this can be when you send something to combustion to produce energy. So for instance, many organic chemicals that go to a waste stream because it's not pure enough, because there is a mixture that we cannot sell. Instead of going to any other thing, you send to a furnace, you produce power. This is the end of life of that stream, for instance. And basically, we can go for different sectors, and each sector actually produces a number of waste. Those can be go to liquid or gas to atmosphere, and depending on the composition, go, for instance, CO2, capture of CO2. That's another example in the end, which is the concentration of the CO2 in the stream, which is the technology that we are going to be using to capture it. So it depends on if it's coming from a flue gas, if that CO2 maybe, because it comes a moment when that thing maybe is a mainstream instead of a waste.
Mm-hmm.
If the composition in one chemical is 90-something%, is no longer a waste. It's something that we can recycle. And it's something that the end of life is going, the post-recycling scenario, what can we do with that? So depending on the composition, it can be a waste that we have to deal with, or it can be a resource that we can reuse. And that's something related to the flow, the amount, and the composition. And that's part of the information that we are gathering in this analysis.
Absolutely. So maybe, because you've just talked a little bit there about the concentration in the flow and how this could then be something for recycling, maybe this is a point now where we could just briefly talk about, I mean, most people, when they think about recycling, obviously it's depending on what kind of material we're talking about, but when we're talking about recycling of chemicals, how is this achieved? Which chemicals, is it possible to recycle all chemicals? Are there some chemicals you cannot recycle? Are some easier to recover than recycle than others? If so, why?
Basically, it depends on the stream. So if you take a look at the chemical industry, actually it's quite integrated. Actually, most of the streams are exhausted until the moment when you can actually send that liquid to first wastewater treatment plant, later to the rivers, or the gas goes through any treatment to remove particles, to remove odor, basically that are organic chemicals, and later you can burn it or just throw it to the atmosphere. So in the end, the idea is to identify which are the chemicals that remain there. So because at some point, if the companies, typically the problem is that you need to create a policy so that you force the companies to report that, so that you know what is in their waste streams. So by doing this, we can identify that, for instance, we don't have data from one particular sector because it's not reported. So in that case, you can, not we, but actually in this case, it was the US EPA has the information to say, okay, it's interesting for this sector that we are missing this particular thing. Why not reporting this? Or it comes a moment when because we're talking about thousands of chemicals. At some point, one particular chemical has been verified that is not is not risky for health. Maybe at some point we can forget about that because it has been proven that that chemical that was new, it was proven that is no longer an issue. Okay, because at that point we decide, okay, this doesn't require to be tracked again or tracked anymore. So this is the kind of the power behind these tools, actually, to be able to analyze which is the data that we need, which is the data available, and in some cases, exactly, if it's not reported or if not reported the way that is useful for the calculation, for instance, the emission factors. For the emission factor, you need information. If you don't have it, so maybe you can say, okay, we need to ask the companies or the facilities to report this kind of information. Position. So this is actually, remember that industry and inventions always go ahead of policy. So by doing this, we can go back and suggest policy.
And perhaps just a question about I know that you obviously used you discussed a little bit the data engineering approach that you used. With the rise of things like machine learning, artificial intelligence, things like this, do you see some opportunities that could be incorporated within your structure?
Actually, they are, because in order to create models to predict the use of a particular pollution abatement unit, or to predict which is the particular end of use of a waste. Actually, I think it was the last work. It was not included because it was not kind of the history before this, but actually those models are available in the last, I think it was the last paper from Jose Daniel's thesis, where we developed those models based on machine learning in the end, because there are a large number of variables involved, and in order to fit the model, actually we were using machine learning. Those models, again, they are available for the public. They are available for any one of you to take a look and use, because the databases are there. You can access it, and actually the code is prepared for accessing those databases and the models developed. They are summarized in the different, typically in the supplementary materials of the papers, because in the end, the papers, you are limited by space, but you have the information. And this is also really important, because when you talk about machine learning, in the end, it's good that you can report the actual models. And the actual models in machine learning will rely on what is the data available and how that data is used, which are the functions, which are the methods used to develop the models. And in this particular case, behind all this presentation, you can have those available because are in the GitHubs of the reported in the papers.
Fantastic. So we'll highlight that. We'll shout that out, that it's worth checking out those models if you're interested in those. So switching now to our Q&A chat, we have a question here. I don't know if this is something that you've covered, but how can we handle nuclear waste?
Actually, I mean, we didn't include that in any of these results, but basically, in fact, if we have previous data, the models can suggest how. So the thing is data driven. So in the end, you need previous technologies used for treating, and we need data reported. Sometimes the problem with the data of a particular sector is that is somehow classified by different governments because it's national security or so on. So if you don't have access to that data, we cannot produce those models. But the methodology is actually useful for that. In the end, if there is information related to different waste streams from different nuclear power plants, and later what they do with them, in the end, we can use that to suggest one treatment based on. So again, this is data-driven. We haven't, only in the pollution abatement units, we were using also somehow the typical chemical engineering approach to evaluate the yield and so on. But most of the other work is just the data that reports this amount, these flows are typically treated in this particular technology. This amount of material is typically burned to produce electricity. So the answer to that question is, maybe we should ask Daniel, but it's not in the ones we've reported. I don't know if it was not covered by the analysis, or basically it was not available in those. Basically in the TRIs, the toxic release inventory, and the chemicals that are there, basically we needed to know if radioactive material was included, or if it wasn't included, was why. Maybe it was part of the secret of the different countries, because in the end you realize that most power facilities in all countries in the world are actually protected, because are key installations for the everyday use of the country. So that, at some point, exactly, one of the issues can be that the information may not be available publicly. That was one of the things that I mentioned twice in the presentation, but that doesn't mean that this methodology cannot be used. It's only that we needed that data.
And the second question here, first the comment, nice talk, Mariano. How chemical regulations can support evaluating the EOL stage impact to the environment and human health?
That's actually, just to say, Gerardo is a co-author of this, is the one responsible from the US EPA, also a very good friend. It's a nice question, Gerardo. Let me try to go a little bit about that. Basically, again, technology goes ahead of regulation. So what we can do with this is, the moment we have the data, try to use that data to evaluate, to suggest policy, in the sense that if we identify the release of certain chemicals that have an effect on the environment, in that case, because they are reported, we can try to pass law to say, okay, if there is an impact because of amount of residue emitted, in that case, we have to pass a law that says you cannot emit more than this. In a different way, we can relate the amount with the impact. As long as we have information on the concentration and the effect of that concentration on the environment, CO2 concentration on the atmosphere, and that the effect of that on the temperature, for instance. As long as we have that, also we can predict that if we continue producing this, that will be affected, because again, it's a data driven. So in the end, if we have that information, we can go and try to suggest a path or a guideline to reduce, because we identify an impact. So if we identify an impact, we can say, if there's that amount of flow, if this concentration, we need to control it. And in that case, go back and go to the policy makers and say, this is what we found. In order to solve or to address this issue, there should be a law that says this. Actually, this is the machine learning that you mentioned before, that trying to relate the amount of waste to the impact. For that, in human health, basically there are a number of course, people working on the side effect of chemicals, the side effect of pharma on the patients and so on. So that kind of information can be used to develop a model that will allow us to relate the concentration of the amount in human health. For instance, if this a particular concentration in one particular location, and if we can have information and we can develop a model to relate that release with the problems in human health or in the environment. For instance, algae blooms. The algae blooms in one particular lake are related to the amount of phosphorus, the amount of other nutrients. If those nutrients we can track the nutrients all from the facility or for the business that generate all the way to the environment. We also are tracking the amount. We are tracking the amount of chemicals that are, so we can see the result, which is the algal bloom, and the amount of chemicals that have to reach. So we can develop such a model for that and go out to say, okay, you should not be, and not only this could be one case, but for many different lakes all around different countries with the different conditions, we can produce a model to say this is important across country, across location, to say, okay, with this amount of chemicals in this condition, there is no algae bloom. In these other conditions, it's generated. So we can suggest policy based on you should not go above this concentration if, for instance, the temperature in the area is this, the water temperature is that, etc. So we can use this model to generate at least a guideline for policy to avoid environmental impact or impacting human health.
And our final question for today, Mariano, we do not have air pollution data for most African and Asian countries. How could you determine their data or the pollution data?
Exactly, I mean, that's important. I mean, if you don't have data, the only thing that you can do is extrapolations. And actually, this is also a risk. I mean, because if you don't have data, you don't know how the facilities are working. And if you don't have the facilities, the only thing that you can go is back to the first principles and see what are the technologies installed and how those technologies are typically working. That can be somehow inferred or calculated from previous results, but we will not be sure that that particular technology will work. But this concept this can be done only through expert evaluation, of course, first principles, chemical and environmental engineering, so that based on the typical operation of those technologies, we can try to estimate the amount. But of course, again, it's a data-driven methodology. If you don't have the data, the only thing that you can do is estimate. And that's also the reason why we presented the 5 different classes of data. Just estimation, informed estimation, because there's expert data, experts that can estimate that those values, but it comes a moment when you should not be using the data because it's not reliable. So if it's not reliable, the only thing that you can do is through first principle, try to estimate what that particular technology, that particular facility may be generating. But in the end, what should be suggested is for all these facilities to report the waste to the country, to any other, let's see, I mean, of course, most of the information would be national level, but if that is available, it can be used. If you don't have the data, you only can go to the first principles and try to estimate what is in there.
Very nice. Thank you so much for that presentation, Mariano. I really did find it very interesting. And for me, it's a real eye-opener. It's certainly something new for me as well. So I very much enjoyed it personally. I will now just share my screen again to provide the final points. So in terms of our closing remarks, the next presentation will be from Joe de Wolf from Ghent University in Belgium. He's going to be speaking with us on the topic of contribution to inaccessibility as resource impact method, resource management along the life cycle. Now, our speaker for Thursday week, i.e. 2 Thursdays from now, we've shifted to July. So the next presentation will in fact be approximately 1 month from now, Thursday, June the 20th, 2024. Be sure to join us for that one as well. Yes, a final big thank you to you, Mariano. Thank you so much for joining us today. It was really a pleasure to have you with us. I see some applause emoticons there. Indeed. Yes, so thank you to everybody, and looking forward to seeing everybody next time. Thank you again, Mariano.
Thank you very much for the opportunity.